Okay. When you hook these up, if you've ever hooked up a battery to a voltmeter and then kind of reversed the electrodes, you'll notice that you get the same potential. It's just that it's deemed a negative potential in one direction and a positive in the other. So in determining which way is going to give us a positive cell potential, the spontaneous direction, meaning the one where the cell that has the higher reduction potential is being reduced, that means that's which way it's going to go spontaneously, that will give you a positive potential, cell potential. Okay, in describing a galvanic cell, like if you were given a redox reaction and asked to describe the galvanic cell in which this would occur, there are 4 things that you need to include in that description. 1 is, what's the cell potential going to be? 2 is, show the direction of electron flow. 3, you need to designate which compartment is the anode and which is the cathode. And 4, you want to put the nature of all the components, solid, aqueous, gas, whatever they are. Okay. Okay, so say this is our half reaction. Okay, here they've done the work as far as finding our, looking up our cell potentials or our standard reduction potentials for us. So now in looking at and comparing these two, then we know that this will be the reduction, and that the iron so my E naught here is going to be positive 0.44, and so we should expect then an E cell of 1.95. Okay, and let's see if we're going to show this. This would be what we would show, and we would have that our E cell is 1.95 volts. Show the anode and the cathode. Show I have a solid iron electrode here with iron ions in solution. The electron flow from the anode to the cathode. And over here, since all of the species for the reduction reaction were all aqueous, then the electrode that I use is going to be one that contains some sort of inert metal, platinum most commonly. So we would have a solid platinum electrode here, and then all of the reduction species are in solution. Okay, there is a simple way of abbreviating this. It's called line notation. This is also used to describe a cell. So we put the anode on the left, the cathode on the right. Okay, you put a single line between different phases, and then a double line in the middle. This double line right here represents a porous disk or a salt bridge. And then again, if everything is aqueous on one of the half cells, you're going to use a platinum electrode. And so for the one we just did, this would be the line notation for that cell. And so this conveys the same information as the drawing did of the cell. Okay. When we're talking about our potential difference, we express that in volts, and a volt is defined as a joule amount of energy per unit of charge, which in this case is a coulomb. So a joule per coulomb is the definition of a volt, which is our unit of potential difference. Okay, in the last chapter we looked at the concept of free energy. And so here we're going to look at delta G is the maximum amount of energy that I'm able to get from a given redox reaction. And the value of delta G is going to be based on the number of moles of electrons that are being transferred, the number of coulombs per mole of electrons, and this is a constant value. This is called Faraday's constant, and it's 96,485 coulombs per mole of electrons. And then E naught is our cell potential. Okay, so here if delta G is the negative NF E naught, and remember delta G negative value means that it's spontaneous. Okay, let's look at an example of calculating the free energy for a given set of half cells. So here we've got copper and iron half cells, and there's an error here because the reduction potential for the iron should be minus 0.44. So as the equation shows, and as the reduction potentials show also, the copper is going to be reduced and the iron will be oxidized. And so my E naught for this is going to be, see, the iron will be oxidized, so its sign is flipped. So 0.44 volts plus 0.34 volts for the copper, so 0.78 volts here. So my delta G is going to be, the N will be 2 when I multiply through to get the number of electrons the same. 2 electrons is going to be, will be what was transferred. Faraday's constant, 96,485. And so that's coulombs per mole of electron. 2 is the moles of electrons. And then my E cell is 0.78 volts. Okay, and so that's going to give me joules for my final value, or final unit. So 2 times 9685 times 0.78. So I have 150,516.6 joules. And whoops, negative. Forgot my negative sign in there. There you go. So this would be spontaneous, and that would be the maximum amount of energy available from this half cell, or from this set of half cells. Okay, so far we've looked at redox reactions that are occurring because of a difference in the affinity of different substances for electrons, that each half cell is attracting the electrons, one more strongly than the other, and so we get that potential difference. But there's also another way that we can connect half cells and get a potential difference, and these are based on differences in concentrations. So a concentration cell is going to have the same components in each compartment, but the concentrations are going to be different. And if you want to think of it this way, remember when we looked at osmosis and how we had the flow of our solvent particles through a semi-permeable membrane going from the more dilute into the more concentrated. And so there was this this push to achieve equilibrium and by getting the concentrations the same. And so this is kind of a similar situation where we have these cells at different concentrations, and the way that it's going to get the concentrations equal is through oxidation and reduction reactions through the movement of electrons. And so that's going to provide the electromotive force in these concentration cells. Okay, so here's kind of an example of one here. So I have, in this case, a more dilute solution at the anode, in the anode compartment, and a more concentrated that becomes the cathode. Now, why do we have these designations? Well, how can this reaction occur to equalize these concentrations in the two half cells? Well, one, I need to reduce the solute in the more concentrated one and increase it in the more dilute one. So in this case, here I want to take the silver metal on the electrode and make more silver ions, and on this side I want to take silver ions from the solution and reduce them into silver metal on the electrode. So we're going to have these two reactions occurring, and they'll keep occurring until the concentrations in each cell are equivalent, and then we no longer have any kind of electromotive force. There's no potential difference between the cells at that point. Okay, so qualitatively, let's look at how we can predict a change in our cell potential from LeChâtelier based on differences in concentration. And here we're not dealing with just concentration cells. Here we're just looking at what if our concentrations are not the standard concentrations. So here what we want to do is predict if the E cell is going to be greater or less than E naught. E cell, notice no naught there. That means E cell is the cell potential when it's not at standard conditions. So we're just going to look qualitatively. Well, first let's figure out what the heck's going on in this. Here we have the aluminum is being oxidized. All right, so let's just do a little picture here. Here I have my aluminum is being oxidized. And so normally, and then my manganese, so aluminum plus 3. So we have flow this way, okay, Al going to Al plus 3, and here I have Mn plus 2 going to manganese. Okay, on that side. So let's think about what's going to happen. If the concentration of the aluminum is increased, aluminum ions. So that's this one right here. If I increase that one, what's it going to do? It's going to shift it back in that direction, back towards the reactants, which is basically going to decrease my cell potential. Okay. Spontaneous flow of electrons is in the forward direction for this. And so here, this is going to be less. If I cause it to reverse, if it shifts back to the left, then my new cell potential will be lower. Okay. If it's increase the manganese ion here, I'm going to shift it right, and there my cell potential is going to be, it's going to be greater than at standard conditions. Okay. And then if both concentrations are increased and they're equal, we would expect that we're not going to have any change. Okay. So that's kind of a qualitative look at how changing the concentrations away from standard conditions can affect the cell potential.